Hello, in this video I'm going to look at a question with variable acceleration. We've got variable forces going on here, and this is really highlighting the point that we can apply these concepts of dynamics, Newton's laws in particular, in a variety of situations and problems that we're going to be solving. But we come to a point where our maths really needs to be up to scratch. Not everything is going to be really simple algebra. We're going to get more and more calculus dripping into our solutions here. So if you're going to be serious about physics, you have to be serious about your maths. You have to have good algebra and good calculus skills. So we're going to see that in this question. We've got a stone of mass m falling vertically downwards under gravity through still water. At time t, the stone has speed v, experiences a resistance force of magnitude lambda mv. So the resistance force is a function of the speed. Lambda is some kind of constant. Now that might have something to do with the viscosity or something of the liquid, of the water. So let's draw out our, what's going to be a fairly simple force diagram. We've got our single object falling downwards. We've got our weight going down, which is going to be mg, and then we've got our resistance force opposing the motion, which they're saying is lambda mv. We can mark on our acceleration. It doesn't really matter which way we draw our acceleration arrow, but yeah, I'll draw it going downwards. It doesn't really make too much of a difference. Now we need to show this differential equation here. So we're going to be applying Newton's second law. That's our connection between force and acceleration. So let's go with that. We do F equals ma. So our resultant force is going to be mg minus lambda mv. That's going to be equal to our mass times our acceleration. And of course, acceleration is dv dt, just keeping an eye on what they want to actually see in our final answer. And now we just got to divide everything by m, and then we've got exactly what they want. So I'll just shuffle everything into the same order. So dv dt is g minus lambda v. So that's a fairly straightforward start where we're just applying Newton's second law. Now they're wanting us to solve this. We can see they've given us the initial speed of the stone is u. So that's saying, when t is equal to 0, v is equal to u. So these are our boundary conditions for when we do our integral calculus. Find an expression for v at time t. So we're solving this differential equation. So we need to be used to how we're going to separate our variables out here. We need to get, this is essentially one expression we're going to have to treat here. If we've multiplied through by the dt, we need to get our v's onto the dv side. Well, we're only going to be able to do that if we treat that all as one expression. So let's put in an intermediate step just to make that a bit clearer. If I've written that dv is g minus lambda v dt, well, the only way to get this v on the right hand side over with the dv on the left hand side is to treat everything in the bracket as one expression. So we're going to end up with an integral which is 1 over g minus lambda v integrated with respect to v is going to be the integral of dt. Now we can put in the limits here. So we've got u for 0, and then we've got our general v at general t. So we've separated those out. Now we need to solve all of this. We've got a log integral on the left hand side here. So we're going to have a minus 1 over lambda natural log of g minus lambda v. That's our integral on the left hand side, and this is why you need to be pretty slick at doing your calculus. That's between u and v, and then that is going to be equal to t. So I'm running out of space here, rather annoyingly. So the 1 over lambda bit, I mean, that's just that's a constant that's going to appear throughout the left hand side, so we could just shove that onto the other side straight away, because it's going to appear in both of our terms when we fill in our u and our v. So let's shove this, let's get rid of this and put it over here, minus lambda t, and that's going to make things a lot easier here, because we're going to have two natural logs, one taken away from the other. So we're going to have a natural log of g minus lambda v minus the natural log of g minus lambda u. So g minus lambda v divided by g minus lambda u, just doing our log laws, is going to be equal to e to the minus lambda t. And now we've just got to kind of squeeze things up into here. We just need to rearrange everything now to make v the subject. So that means we're going to have g minus what have we got? G minus g minus lambda u over e to the lambda t, all divided by lambda, is going to be equal to v. So that's just rearranging everything we've got there to make v the subject. So some fairly straightforward algebra that we need to do at the end. But yeah, there's a lot to get used to in here. You know, you want to be doing, I know some people might be thinking I've left out some steps there. I mean, that's partly to do with the fact that I was running out of space on the page, but also that you should be at the stage where you can do this algebraic manipulation as quickly as this. You don't need to write out every step every single time. Okay, if you're sitting in an exam, then maybe you'll want to be a little bit more thorough. But it's not, it's not a great leap to be able to, go through this integral in just a handful of steps in that way. And similarly with your integration, you don't want to be looking at this integral and just not knowing where you're going. So you need to be really slick on your calculus, and you need to be really slick on this algebraic manipulation. So when you're building up to be doing algebra in this way, then yeah, write out in steps every step as you're going through, multiplying through by the g minus lambda u, and then rearranging things, and then dividing by the lambda. You can write all of that out, but then go back through it again and see in your mind what steps you've actually taken and visualize it. It's just a different way of looking at it after the event to see, oh yeah, these are the steps that I've taken, because they're always the same steps. It helps you to improve your algebra if you're more conscious of what you're doing, rather than just thinking, oh well, I'm aimlessly or facelessly, not aimlessly because you have got an aim, but facelessly just going through these same steps every time, thinking you have to write everything out. Yeah, it's just slowing you down really on these things, and you should be able to get your algebra up to a level where you're not needing to do that. So yeah, the question itself isn't that interesting. It is quite easy to solve. It's a maths problem really, rather than a physics problem, because the physics concepts in it are quite straightforward. But I really want to emphasize that importance of being good at algebra and calculus.